You spend weeks, maybe even months, tuning your transformer architecture. You tie your input and output embeddings because, you want to save that massive 30% chunk of GPU memory.
Oh, absolutely. It's just standard practice. You need that VRAM.
Right, exactly. So you tie the weights, you load up a massive text data set, and you just let the model rip. And you watch the loss curve, and it looks pristine. It's going down exactly like it should. Everything seems totally optimal.
On the surface, yeah. The metrics are telling you everything is fine.
But under the hood, inside your high-dimensional embedding space, there is this silent, severe geometrical collapse happening. Almost every single word vector in your massive vocabulary is actually pointing in the exact same direction.
It's terrifying when you actually map it out.
It really is. The semantic representation power of your model is basically just bleeding out, and your standard loss metrics are completely masking the problem. So for today's deep dive, we are unpacking the foundational 2019 ICLR paper, Representation Degeneration Problem in Training Natural Language Generation Models.
And this paper, it is just a masterclass in challenging the default mechanics of natural language generation pipelines. It really is.
Okay, let's unpack this.
Yeah.
Because the authors isolate this exact phenomenon, right?
Yeah.
And it really shakes up what we take for granted.
Yeah, completely. When we train these models, we take certain optimization tricks as, well, basically settled science.
Like gospel.
Exactly. We just assume that as the cross-entropy loss goes down, the continuous vector representations we're learning are naturally organizing themselves. We assume they're building this rich, uniformly distributed, latent space.
Right, like the vectors are spreading out nicely to capture all the maximum semantic and syntactic variance.
Yes, but what this research mathematically proves is that our standard training practices actually force the complete opposite to happen. The word embeddings actually degenerate.
They collapse.
They do. They cluster tightly into this highly restricted, tiny region of the latent space that the authors define as a narrow cone.
A narrow cone. I love that visual. But I think we need to really visualize the specific geometry of this anomaly to understand why it totally breaks down model performance.
For sure. Geometry is everything here.
So if you, the listener, consider the embedding space as this high-dimensional sphere, the optimal state for expressiveness, what we actually want, is an isotropic distribution.
Meaning you want vectors pointing in all possible directions.
Right, because the angles between them are what effectively encode the semantic differences. But this degeneration, this narrow cone effect, it's like forcing every single vector to point roughly toward the North Pole of that sphere.
Yeah, that's a perfect way to picture it.
So the entirety of the southern hemisphere, the equator, it is all completely devoid of vectors, just empty space. So if all these vectors are crammed into a narrow cone at the top, how does this geometric collapse specifically limit the representation power of the embeddings?
Well, the immediate casualty of that geometric collapse is the model's ability to express nuanced probabilistic differences, specifically during that final prediction step.
When it's actually trying to guess the next word.
Exactly. Think about the pre-softmax layer. The model generates a hidden state vector representing the current context, right? And then it computes the dot product between that context vector and literally every word embedding in the vocabulary matrix.
Standard matrix multiplication.
Right. And the model heavily relies on directional variance. It relies on the angle between the context vector and the word vectors to separate the highly relevant tokens from the completely irrelevant ones.
But wait, if every word vector is jammed into that narrow cone pointing at the North Pole, their directional variance is functionally zero.
That's exactly the problem. The context vector is going to have a highly similar positive dot product with almost the entire vocabulary.
Oh, wow. So regardless of actual semantic relevance, the model basically thinks everything is a decent match.
Yes. The optimization process is then forced into this awful corner. Since it can no longer rely on the angle to differentiate between words, it has to rely almost entirely on the magnitude.
The L2 norm of the vectors.
Right, the L2 norm. It uses magnitude to push the target word's probability higher in the softmax layer. It literally artificially lengthens the vectors of certain tokens.
So it's compensating. When directional semantics are lost, the representation power is fundamentally degraded, and it just tries to brute force it by making the vectors longer.
Yeah, and because of that, it struggles heavily to output low-frequency words. It defaults to high-frequency tokens simply because the training process has pushed their vectors to have larger magnitudes.
Just to compensate for the lack of angular separation. That is wild. So if the model is compensating by artificially extending magnitudes, the root geometry is severely broken. Which brings us to the mechanics of the collapse itself.
Right, the why.
Because the authors don't just, observe the cone and walk away. They diagnose the specific training conditions that trigger it. They identify this perfect storm of three factors.
And those factors are likelihood maximization via standard cross-entropy loss, the weight tying trick, and the highly skewed token distribution inherent to large natural language datasets.
Okay, let's hone in on that. Because the weight tying trick is standard practice. Is the paper actually arguing that this very optimization trick, the thing we use to make training on big datasets even computationally feasible, is exactly what causes the vector space to collapse?
What's fascinating here is that, yes, the paper proves exactly that. It analyzes these precise conditions and shows a direct mathematical link. Let's look at the gradient dynamics of that combination.
Specifically, how likelihood maximization interacts with the dataset distribution, right?
Yeah, the Zipfian distribution. Under cross-entropy loss, the softmax function operates as a strict zero-sum game. When you compute the gradient of the loss with respect to the word embeddings, the target word gets this positive update.
It's proportional to the hidden state, right? Pulling the target vector toward the hidden context vector.
Exactly. But simultaneously, because it's zero-sum, every single non-target word in the vocabulary gets a negative update. It pushes their vectors away from that hidden state.
Okay, this is where we can apply a sort of gravitational analogy. Because word frequencies in big data sets like Wikitext 103, they follow Zipf's law.
Right, a tiny fraction of words appear millions of times.
The S, while the vast tail of the vocabulary is super rare. So those high-frequency words are basically acting like gravitational black holes in the latent space.
That's exactly what they are, black holes.
Because they are the target word so overwhelmingly often, their hidden states just completely dominate the gradient updates. The model is constantly pulling the vectors of these high-frequency words toward a specific, dense cluster of hidden states.
And at the same time, it's trying to push the rest of the vocabulary away from that cluster. But here is where the weight tying trick, finalizing the collapse, comes in.
Right, because normally we have an input embedding matrix and output projection matrix, but we tie them.
Exactly. We tie the weights to share parameters.
Yeah.
So we are forcing one single matrix to serve two totally conflicting objectives.
Conflicting how?
Well, as an input embedding, it needs to capture diverse semantic meaning, right? It needs to distribute tokens logically so the model can understand the input. But as an output matrix, it is subjected to those massive, frequent gradient updates from the high-frequency hidden states we just talked about.
Oh, I see. And because the input and output embeddings are physically the exact same matrix in memory.
The intense gravitational pull from the output layer's likelihood maximization just drags the entire shared vector space.
They're toward the hidden states of the common words.
Yes, toward the North Pole.
Wow. So the optimization trick that literally saves us 30% of our VRAM is actively destroying the isotropic distribution we desperately need for actual semantic representation. All the vectors get sucked into the gravity well.
Creating the narrow cone.
Okay, so if weight tying combined with cross-entropy is the main culprit here, the obvious brute force engineering fix is just untie the weights, right? Let the input embeddings distribute naturally, and let the output embeddings handle the softmax dynamics. Problem solved.
I mean, you could untie them, sure, but you would instantly lose the memory efficiency and the regularization benefits that made weight tying a standard practice in the first place.
Which is a huge deal for massive vocabularies. You'd all immediately on modern architectures.
Exactly, out-of-memory errors everywhere. The authors recognized that reverting to untied weights was just not a scalable solution for modern ML. Instead, they realized they needed to mathematically force the vectors apart without actually losing the shared matrix.
So they needed a new regularizer.
Right. They formulated a novel regularizer to add directly to the loss function. It essentially acts as an anti-gravity mechanism against the pull of those high-frequency tokens.
Okay, let's get into the mathematical formulation of that regularizer, because this is where it gets really clever. We need to push the vectors apart to reclaim that lost representation power, which means we need to maximize the angles between them.
Right. Increase the directional variance.
And the authors do this by calculating the cosine similarity between the word embeddings and then basically penalizing the model when those similarities get too high. They're essentially pushing the gram matrix of the embedding matrix toward the identity matrix.
Yeah, that's the core math right there. By taking the embedding matrix, let's call it W, and multiplying it by its transpose, W transpose, You get the Gram matrix.
Which just contains the dot products of all the possible pairs of word vectors.
Exactly. And the ideal isotropic space would have an orthogonal relationship between distinct concepts, meaning the off-diagonal elements of that Gram matrix should, ideally, be close to zero.
Because if the dot product is 0, the vectors are orthogonal, 90 degrees apart.
Right, so the author's regularization term specifically penalizes the L2 norm of these off-diagonal elements. As the likelihood maximization tries to pull everything into the narrow cone, the regularization penalty spikes.
Which forces the gradient descent algorithm to push the vectors back apart to minimize the overall loss.
Exactly, it's a built-in repulsive force.
But wait, so we are forcing the Gram matrix toward the identity matrix. We are mathematically forcing all distinct word vectors to be orthogonal to each other.
Globally, yes.
Doesn't that fundamentally destroy semantic proximity? I mean, if I have synonyms like happy and joyful or related concepts like king and queen, I actually want their cosine similarity to be high. I need them clustered locally.
Of course.
So if the regularizer is just blindly penalizing high cosine similarity across the board, doesn't that ruin the representation power in a completely different way? Like, you're fixing the cone but destroying the clusters.
That would be the catastrophic result, yeah.
Mm.
If the regularizer were applied with too much weight, effectively overpowering the primary cross-entropy loss function.
So how do they balance it?
The authors address this through careful tuning of a coefficient often denoted as gamma, which basically scales the regularization term.
Okay, so it's a weighted penalty.
Yeah. Exactly. The cross-entropy loss is still the dominant driving force, and it is still actively pulling semantically similar words together based on the context. The regularizer is just a soft penalty.
Ah, I get it. It's not strong enough to tear synonyms apart when the cross-entropy loss is screaming at the model to keep them close for prediction accuracy.
Exactly. What the regularizer is strong enough to do, though, is prevent the global macroscopic collapse of the entire vocabulary into a single direction.
So it preserves local semantic clustering while enforcing a global isotropic distribution. That is brilliant. But I have to ask about the computational overhead.
Yeah, the math isn't free.
Right. Computing pairwise cosine similarity for an entire embedding matrix, let's say a standard vocabulary of 50,000 tokens, that requires a 50K by 50K matrix multiplication at every single forward pass.
Which is massive.
It's computationally horrific. You were trying to save memory with weight tying, but you are introducing an O of V squared operation into your training loop. How does the paper possibly justify that compute trade-off?
Well, they don't, because they don't actually do it that way. The paper introduces a critical optimization to make the regularizer computationally feasible.
Oh, thank God. What's the trick?
Instead of calculating the W times W transpose multiplication over the entire 50,000 token vocabulary at every single training step,
Right.
the authors compute the regularization term only over the vectors of the tokens actually present in the current mini-batch, or a similarly reduced subset.
Oh,
Yeah.
okay. Because neural network training happens over thousands or millions of iterations.
Exactly. Applying the geometric penalty to these random mini-batch subsets is statistically sufficient to spread out the entire embedding space over time.
So you achieve the global anti-gravity effect without absorbing the catastrophic bottleneck at every single step.
You get the best of both worlds.
Okay, so we have a mathematically sound, computationally feasible mechanism to dismantle the narrow cone. But theory is just theory. The next phase of the paper moves away from the math and subjects this regularizer to actual empirical validation.
And they selected two very specific testing grounds for this: language modeling on datasets like Wikitext 103 and machine translation on the WMT14 English-German dataset.
The selection of those two specific tasks is highly deliberate, isn't it, for evaluating representation power?
Highly deliberate. Language modeling on Wikitext 103 that tests raw, open-ended natural language generation. The model must generate a coherent probability distribution across the entire vocabulary based purely on the preceding context.
It's totally unconstrained.
Right. Machine translation, however, is a strict context-dependent conditional generation task. The output distribution is tightly constrained by the encoded representation of the source text.
Right, because a regularizer that helps open-ended text generation could, in theory, easily inject too much variance and actually damage the strict deterministic constraints you need for accurate translation.
Exactly. You need to prove the regularization doesn't just hallucinate variance where precision is required.
So does the paper show it improves both?
It does. The empirical results demonstrated robust improvements across both architectural constraints. In language modeling, applying the regularizer resulted in significant drops in perplexity compared to the baseline vanilla algorithms.
And lower perplexity directly indicates that the model's output probability distributions are much sharper, right? More accurate regarding the held-out validation set.
Exactly. The model is literally less surprised by the actual sequences.
And in the machine translation tasks on WMT14,
They saw quantifiable increases in BLEU scores.
which is huge.
It is. And the increase in BLEU scores directly validates the restoration of that directional variance we discussed earlier. Because the vectors are spread out, because the narrow cone is dismantled, the model is no longer forced to rely purely on the magnitude of high-frequency words.
It can finally utilize the specific angular differences.
Yes. It can select a highly relevant, low-frequency word over a common but slightly inaccurate filler word. The translation becomes more precise because the latent space is actually capable of representing precision.
The model reclaims the semantic resolution that the weight-tying trick had just silently stripped away.
It's just a highly elegant engineering solution to a problem most practitioners didn't even realize was happening inside their matrices.
Seriously. So, just to synthesize the contributions of this paper for everyone listening, the authors identified a fundamental geometric anomaly, this narrow cone representation degeneration.
Right.
They mapped the precise causality to the interaction between cross-entropy likelihood maximization weight tying and Zipfian dataset distributions. And then they engineered a computationally optimized gram matrix regularizer,
Which acts as that anti-gravity force.
pushing embeddings toward an isotropic distribution and recovering the model's semantic resolution, all while maintaining the vital memory efficiencies of shared parameters. It's an incredible piece of work.
It really is. And, I think the enduring value of this paper really lies in how it challenges our trust in default optimization mechanics.
What do you mean by that?
Well, we discovered that a standard efficiency practice like the weight tying trick was silently causing severe geometric collapse back in 2019. It forces an immediate, critical question regarding the massive, trillion-parameter architectures that you, the listener, are tuning today.
Oh, that was a great point.
Right. How many of our current universally accepted optimization tricks, our memory-saving hacks, or our distributed training mechanics are silently limiting our model's representation power? And in geometric or mathematical ways, we simply haven't even thought to measure yet.
That is exactly the critical lens we need to push these architectures forward. We cannot treat the standard pipeline as a black box. You have to look at the geometry. Well, thank you for joining this deep dive into the source material. Keep interrogating the fundamental mechanics of the models you build.